It's an honor to have here Professor Rodrigo Quiroga from Universidade Nacional de Córdoba. Thank you very much, Rodrigo. I appreciate your acceptance to participate in a series of talk. Rodrigo, you can start your talk now. Thank you very much for accepting participating.
Okay, thank you, Walter. It's a pleasure and honor to be here speaking in this occasion. My name is Rodrigo Quiroga. I work with Marco Villarreal, who gave the last presentation in the series of talks. And we basically work on developing new scoring functions to perform molecular docking. And so our previous work is called Binardo, and now we are working on the second version of this scoring function, and we hope to publish it soon. But what I'm going to talk to you about today is the pitfalls and advantages of training scoring functions. So I'm going to go into just a little bit of an introduction. What is molecular docking? What is a scoring function? How does it work? And then we will go into some details, some applications of scoring functions, and also what problems you run into when trying to train new scoring functions or use them for a certain application. Okay, so basically, what we do when we are performing molecular docking is we couple a scoring function with a search algorithm. So the scoring function is kind of like a force field, right? Some of you know from molecular dynamics simulations. Well, the scoring function is similar to that. So basically, it's when we apply this function, we are able to calculate or score, which should be correlated with the binding energy of two molecules. In this case, we will be talking about the interaction between small organic molecules, drug-like molecules, and proteins. So the docking process, the molecular docking process, is a computational simulation which attempts to find the most stable pose and place where a ligand or a drug compound will interact with a protein. So the name docking comes from boats, and it's similar because when a boat approaches a dock, they have to find their own place which they should park their boat in, and that place is predefined. I mean, there's just one place where it should go, and something similar happens with drugs. So why is docking important or useful? Well, structure-based drug discovery, you can find sometimes in papers you will find this as SBDD, is faster and cheaper than doing experimental screening for millions of drugs. So when a drug company or a researcher wants to find a new inhibitor for a certain protein that is associated with maybe with a disease or something similar, they can do experimental screening, which is just test all of these drugs in some kind of in vitro or in vivo experiment. But this has a very, very low success rate. So this takes a lot of time and it costs a lot of money. So what you can do is, first you can do virtual screening, which is use molecular docking to predict which of the compounds present in a drug library, in a compound library, have a good chance of being inhibitors of that protein. And coupling this with experimental screening, the success rate goes up by 2 orders of magnitude, which means, the success rate is still very low, it's just 0.1%. But this means that we can make experimental screening up to 99% cheaper and faster than if we didn't do virtual screen. So this has proven successful for a number of drugs already. I won't go into much detail, but I want to propose this concept. Maybe some of you are familiar with the concept of potential energy surface. Well, here is kind of the same idea, but a little bit different, because this surface regards binding energy, right? So we can think of the surface as the interacting energy between the small molecule and the protein, and we define a scoring function which allows us to score any particular system with a set of XYZ coordinates or Cartesian coordinates for each atom involved in the system. But then we also need a search algorithm in order to be able to find the minimums of this binding energy surface, right? Because we expect that this minimum will be the most stable position in which these two molecules will interact. So the first thing to say is that if we allow for a flexibility of both molecules, the problem becomes much harder and more computational resource intensive. So it will take a long time, and we need docking to be very fast, and I will explain in a second why that is. We need it to happen in seconds or less than a second. So in order to have a little bit of a more simple system, the proteins are normally taken as rigid bodies. The atoms of the protein don't move in the computational simulations in which we will be doing molecular docking. So the only thing that is flexible here in the simulations is the ligand. And the ligand, as we said previously, these are small organic molecules, drug-like molecules, and they can move, they can translate, and they can also rotate. There are certain bonds within these molecules which can rotate. So we will explore all those degrees of freedom within these docking simulations. So basically, what we said before, docking consists of the two parts, right? A scoring function, which we'll see different types, which allows us to score a certain pose of the ligand with the protein. And we also have different search algorithms which will allow us to search for the most stable pose. So within the scoring functions, we have empirical functions, which are normally a linear sum of terms in which each of these terms attempt to describe with the potential, a mathematical function, the energy of a certain component of the energy of that interaction between those two atoms. And then, so we have, for example, one component that accounts for van der Waals interactions, another one for a Coulombic potential for charges between charged atoms, and also you can include terms to account for entropy and solvation and different things. Sometimes also many empirical functions incorporate terms for H bonds, hydrogen bonds. So this is one of the most used type of functions, and they have several advantages and disadvantages. One of the advantages is that they're quite simple. They can be quite simple, and they can work at the same time quite well. And we will define in a bit what we mean when we say work or work well. But we also have it also has downsides. For example, to train them, you need a database of protein ligand complexes with a known experimental binding energy. So That is one of the drawbacks of empirical functions. And then we have knowledge-based functions, which use the whole PDB database, which is the database where all protein structures are deposited. We can extract from there all the proteins that have ligands co-crystallized with the protein. And so they use this large amount of structural information to infer probabilities of distances between atoms. And using this idea, they can reconstruct a potential, which a scoring function, which allows us to score any protein ligand complex, any pose of a protein ligand complex. And then the third type is applying machine learning to also perform the three uses of scoring functions, which we will see are scoring, docking, and virtual screening. There are more than 100 scoring functions to date, and there are more and more coming out almost every month. And then, as we said, this scoring function kind of defines the binding energy surface. And then we need a search algorithm which will allow us to search for the global minimum of a system, right? And there are basically two types of search algorithms: systematic search algorithms or stochastic search algorithms. I will not go into too much detail, but some of the most used are Monte Carlo and genetic algorithms. So, as we said, the main application of a scoring function, or the basis of a scoring function, is that it is able to tell us, if we define a pose between a ligand and a protein, it allows us to associate that pose with a given binding free energy, right? And we don't attempt to measure energy per se, but the score that the scoring function gives us is an estimate and is supposed to be correlated with the true binding free energy of that ligand and that protein, right? So the idea is to estimate the energy of what we see here on the slide, of going from a state where each of the molecules is solvated, but there is no interaction between them, and the state where both molecules are interacting, right? And so, according to the methodology which of the scoring function, we have different degrees of complexity. And we have normally the most simple scoring functions are the empirical scoring functions, but this can actually they can be quite more complicated than this, but sometimes they can be very simple and still work relatively well. The knowledge-based scoring functions are a little bit more complex. Then we have force fields that incorporate a lot more terms and a lot more degrees of freedom, because they have parameters not only for atom-atom interactions and distances, but also for angles and torsions. So that's why the number of parameters escalates a lot for force fields. And then we have machine learning, which is complex to say how many parameters they have. We will not go into too much detail about that. So, what do we use scoring functions for? Basically, these are the three main applications. One is scoring, which is basically we have this pose of a protein ligand complex. What is the binding free energy associated with that complex? The second is docking, which is a slightly different question. This is where we incorporate the search algorithm, where we need to now search for the pose of the ligand and the protein that represents ideally the global minimum of that binding energy surface, right? And then we have the third application, which is virtual screening. And now this is a little bit tricky, but here what we want to know is we have a protein of interest, we have many putative ligands, and we want to know which ones of all those ligands have a good probability of being good binders to that protein. And if it binds with a predicted high affinity within the pocket of the active site of the enzyme, there's a very good probability that it would be a good inhibitor. So that's what we attempt to predict. And here, the key difference with docking and scoring is that we will need to have a good idea of how the binding energy between different compounds compare between them, right? So let's go into a little bit more detail. When we do scoring, we basically want to know the free energy of binding or estimate the free energy of binding of a ligand and a protein. So normally what we do is put together a database of ligand-protein complexes. We have the structures for the complexes, and we also have the experimentally determined interaction energy. So this can be determined in different ways, but the idea is that if a function is good for scoring, we say that it should have a good correlation between the score or the predicted binding energy and the experimental binding energy, right? So we normally have graphs that look like this. This is for PDB bind, a database of protein ligand structures, and we normally measure the correlation coefficient or the determination coefficient to kind of rank how good the scoring function is at performing this scoring task. So normally it is important to say that this is normally how traditional empirical scoring functions are trained, right? We put together the scoring function, which terms we're going to add together, and then we have a big table of parameters that, depending on the atom type, will serve to determine how this potential varies between different pairs of atoms according to the atom types, right? So normally what you do is attempt to, one of the things you can do, or the traditional way that empirical scoring functions are trained, is with MLR regression, right? With a regression, we attempt to minimize the error, right? Of a graph like this, where we plot predicted binding energy versus experimental binding energy, and using least squares or linear regression, we can train those parameters to minimize the error in the predicted binding energy. So here I have on the graph two different scoring functions where the black dots are more highly correlated, so they have a smaller error, and the other scoring function, the white dots, is another scoring function that is worse at scoring. At least we normally say it's worse because its correlation, the correlation between the predicted binding energy and the experimental binding energy is lower. So one thing to keep in mind is that when we are doing this scoring, all we care about is how close to the experimental energy our prediction is, right? So here I want to show you that scoring power says nothing about how well our scoring function represents that binding energy, the real binding energy surface. And you can see this very easy in this graph, where these are three made up scoring functions, right? On the x-axis, we have generalized the coordinates of the system. So you can think of this as a one-dimensional representation of the coordinates of each atom in the system, both the protein and the ligand. So on the x-axis, we can find different poses of the ligand within the protein. And then on the y-axis, we have the binding energy, the estimated binding energy of that particular set of coordinates. So, for example, if you look at the scoring function 2, which is in blue, it's a scoring function that has 2 local minimum, and then it has 1 global minimum, which corresponds to the black dot. So this would be an ideal situation where the binding energy surface of this scoring function has a global minimum that coincides with the co-crystallized structure, experimental co-crystallized structure. So the experimental structure is the same or very similar to the pose that represents a global minimum in the binding energy surface. However, this may not always be the case, because all we're doing so far is just saying how close the predicted binding energy is to the experimental one, but there's no guarantee that our scoring function will have a minimum at the experimental crystallized structure or similar structures, and even more so, we could have a maximum there, which would be not good, obviously, right? But that can happen when we train a scoring function only with experimental and predicted binding energies. So I have 3 scoring functions here in different colors. They all have the same scoring ability because they all predict a binding energy that is very, very close or identical to the experimental one, right? So they all pass through the black dot in the center of the screen here, right? So they all have the same scoring ability, but the binding energy surface of each one is completely different, right? So it can be that experimental structure can be very uncorrelated with the global minimum of that binding energy surface. So for example, for the red scoring function, there is another minimum that is very different from that one and has a much lower energy. But since we never explore this binding energy surface, we don't know that, right? So when you train a scoring function only with scoring, this is one of the problems that you can run into. So the overview for this part is beware of using a scoring function trained only on scoring tasks to perform other functions like docking or virtual screening, because the information that you gave, that you used to train your scoring function does not include a lot of information that you will need to be able to be successful at docking and at virtual screening. And for complex scoring functions, and especially machine learning-based scoring functions, training only with the scoring power is very dangerous because it leads to a very degenerate and noisy parameter space. So there are a lot of solutions that achieve very good scoring power, but they have very little physical meaning, right? So this leads us to the second application of scoring functions, which is docking, right? So here we want to reproduce and have our scoring function and search algorithm find a global minimum for this system that is as close as possible to the co-crystallized experimental structure, right? And so what we do is we allow the ligand to move and rotate within a certain box. We have the protein in this box, and we will look for the global minimum. And when we find that global minimum, we find several minimums. Sometimes we can do maybe 5 or 10 different local minimums, and we look to see if those local minimums correspond, or how close are they to the crystallized experimental structure. If you have the first one, the global minimum that you found, or the minimum that you found is very close to the experimental structure, we say that is a top one hit. Or if the first one is a different structure to the crystallized one, maybe you can find a similar one to the experimental structure in the top 3 or the top 5. So normally we will talk about docking power. We will say what percentage of the test structures our scoring function was able to find a global minimum that coincides with the experimental structure. So if we can do that for 50% of the structures, we say it has a top 1 docking power of 50%, for example. So, but another thing to keep, if we think about this kind of binding energy surface, we can think about a high scoring power and high docking power scoring function, which is this example, for example. This is this is the binding energy, predicted binding energy or estimated binding energy for different conformations of a single system, a complex of a protein and a ligand. So we could explore this binding energy surface with different methods. And what we do is this is theoretical. We can't really do this, or we normally don't do this. But we can find several local minimums, and we can find the global minimum for this scoring function corresponds to a structure that is very similar to the experimental structure. So, as we said before, if that dot on the bottom, the green dot here, is a binding energy that is similar to the experimental binding energy, then that would be a good scoring, high docking scoring power, scoring function. But also, if that minimum corresponds to the minimum, the global minimum of that scoring binding energy surface, then we say that it also has high docking power, because it can find a structure that is very similar to the experimental structure using this combination of a scoring function and a search algorithm. But sometimes, as I said before, a scoring function could be very good at scoring, which means that the predicted energy is very similar to the experimental one, but the binding energy surface has local minimums which have a lower energy than the structures that are similar to the experimental structure. So in this case, when we do the ranking, we order these minimums by their energy, and we can see that the top one will be the red one, the local minimum 1, then will come the orange one, the local minimum 2, and then only in the third position will we have a structure similar to the experimental one. So this scoring function doesn't have as good docking power as the last one, right? Because this would be a top 3 instead of a top 1, right? Yeah. But it maybe has the same or even better scoring power, okay? And then there are a few caveats. Normally when we talk about successful docking or similar structure, what we do is we measure RMSD. So this is a measure of the root mean square deviation of the positions of the atoms. And so when two poses of a ligand are identical, the RMSD is 0. And if they are very different, that goes up to infinity, right? So normally what we do is we say if the RMSD is lower than 2, then the docking is successful. And if the RMSD is larger than 2, then those two structures are not very similar, so the docking is not successful. And this has a few problems. First of all, the threshold is questionable when you apply it to both small and large ligands. For small ligands, it's okay, but for large ligands, sometimes we have situations like we can see here in the left, where the docked ligand is in light blue, and the structure, the experimental structure of the ligand is the white one. So you can see that the part that is deeply buried within the pocket of the protein, the active site of the protein, is almost identical to the experimental, between the simulated and the experimental pose. But this part of the ligand that is more exposed to the solvent is different. But of course, this part of the ligand does not interact very much with the protein, so it would be expected that this moves more, right? So the 2 angstrom threshold is, you have to take it with a grain of salt, as they say. It's not that simple sometimes. And the other thing that can happen is if you have ligands that are symmetric or partially symmetric, you can get very large RMSD values, although the actual structures are not that different. For example, here you see a ligand that is docked the other way around. So in the experimental structure it's like this, and in the docked structure it's like this. One has the oxygen towards the inside and the other towards the solvent, but the RMSD value is very high. So those are 2 cases where you have to take pay some special attention sometimes to the RMSD values, and we have to think about better ways to measure this docking success. And one of the things that we are implementing is this program called SUCOS that partially solves some of these problems. You can, if you're interested, I suggest you look up the paper for that. So, and the other thing to remind you is that sometimes one scoring function, the normal case is when we use one scoring function to generate local minimum, and then we use the same scoring function to score those local minimums, and then we rank those according to predicted binding energy, and then we see which of those structures is close to the experimental structure, right? But in some cases, what we do is different. We generate the minimums, the structures that represent local minimums with one scoring function, but then we use another scoring function, sometimes a machine learning based scoring function, to predict the energy of each of those structures. And here there's a problem, because as we said before, what you could have is a surface, a binding energy surface that looks like this, where the actual global minimums and local minimums are not are not close to the experimental structure. And actually, what we are measuring, this structure here in red and this structure in orange, they were generated because the scoring function on the left had them as local minimums, but this other scoring function, they might not even be a minimum, right? As we said before, they could be anywhere, even at the maximum. And so when we use a different scoring function to evaluate docking power, this is complicated because we can have this kind of example where we think the scoring function is very good at representing the binding energy surface of this complex, but maybe that's not true. Maybe we are seeing an artifact of this scoring function that is supposed to be good, but it's actually because we are not exploring the binding energy surface of this second scoring function. Because sometimes we can do that, or it's very difficult to do that. So we have to be careful when we use one scoring function for scoring and another for docking. Well, that's the same thing we said. Very careful when you see this, and also sometimes a higher RMSD value is actually a successful docking. It could be considered successful. Sometimes you have to go and check the actual case, look at the details, and then also the parameter space in which scoring functions can perform well in auto-consistent docking is much smaller than for just scoring power or docking power, right? So there's only a certain set of parameters that will allow you to both dock well and score well, right? And sometimes that is a good thing because it means the scoring function has a binding energy surface that is approximately similar to the experimental one. And many times, if we just look at the docking power of a scoring function, we can be tricked into thinking that a scoring function works better because it has higher docking power, but it was because of what we saw before. Sometimes these are machine learning functions that only score certain poses, but we can tell that they are bad and they are using non-physical terms, non-physical interactions, non-physical scoring, and they achieve very high scoring or docking results simply because they are not doing both things. So you have more liberty within the parameter space to make a scoring function good at doing one thing, but this can be tricky, as I said before. So lastly, the most used application of molecular docking and scoring functions is virtual screening. And virtual screening is where we take a whole bunch of compounds and we mix. Well, what we want to do is of those millions of compounds, we want to know which ones have more probability of being possible inhibitors of a certain enzyme normally. And this is the application. But we can also train and test our scoring function's ability to perform virtual screening. And to do that, we have a set of active compounds, a set of inactive compounds or decoys, and we do a whole lot of docking, millions of docking experiments, simulations, and then we see how high on the energy ranking or score the active compounds are, right? So, to give you an idea, some very used libraries are Sync20, which has 230 million compounds, and Enamine Real, which has, this is actually billion in Spanish, so it's 6,750 million compounds for Enamine Real. So these are huge libraries, and this is why I said in the beginning that we aim to have scoring functions that work very fast, docking programs which work very fast, because here, for this application, we need to run millions and millions of times. And the ability to perform virtual screening successfully, it depends on the scoring function being able to, first, correctly dock each compound, find the global minimum, which should correspond to a structure similar to the experimental structure, and then they need to correctly estimate the binding energies and be able to compare between different compounds, binding energy of different compounds to the same protein. This is quite difficult, and then we ask ourselves how high, when we try to train or test our scoring function for this application, we say how high are the active compounds ranked. The higher that they are ranked, the better we say that our scoring function works for this application, for virtual screening. So in a way, you can think of it like this. We have a set of binding energy surfaces for each complex, ligand-protein complex. And theoretically, you can think of it like this. We find a local minimum. In this case, we only find, it's a simple example. We find 1 or 2 minimums for each compound. And we measure the binding energy, we estimate the binding energy. And in the best of cases, this is what happens. Our active compounds are predicted to bind with a larger binding energy than the decoys, right? So this would be a successful scoring function for performing virtual screening. But the problem is that there are several problems. One is that, again, for this application, many people have developed machine learning scoring functions which take the pose or the structure of the complex generated with another scoring function, and they score those poses, and they are able to achieve better screening power. Well, this is very complicated because here we're using, you can see that decoy 1 has the same x coordinates in both graphs. So this is one scoring function that we use to generate all the structures that correspond to local minimums, and then we compare the energies of those minimums. So the lower that a dot is, a minimum is on the y-axis, it means that the binding energy is greater. So this scoring function works well, and it predicts the active compound to be better at binding to the protein than these decoys, right? So it works okay. And then here what we do is now we score those structures with another scoring function, right? So now this scoring function has we have no real way to restrict the scoring function to still have a minimum at these positions, at these coordinates, right? So we only score this pose, this pose, this pose, and this pose. These 4 poses. So the new scoring function looks like it has the same ability to predict, to perform virtual screening as the original one, but actually, if we used this scoring function to explore the binding energy surface, we would find that maybe now these decoys have other positions, other coordinates, other local minimums, which are lower in energy than the position for the active compound. So now if we would actually explore the binding energy surface, we'll find that this is a worse scoring function for performing virtual screening than the original one with which we generated the structures. But we will never know, especially if this is a machine learning function. So there's a problem here. And it is by far virtual screening the most demanding application because it needs to find the correct minimums, the correct structure for each protein ligand complex, and it needs to be able to predict the binding energy, and it needs to be able to compare adequately the binding energy of different compounds which can have different sizes, different atom types, different chemical groups, etc. So one thing is that for when you train a scoring function to perform this task, you need to be careful of removing the biases that are possibly present in these data sets. And you need to be for example, .E is a data set that is very used for benchmarking virtual screening scoring functions, and we know that it has already been published that it has biases, and when you use a machine learning scoring function, you can accidentally train your scoring function to find those biases, because sometimes, normally, the inactive compounds are generated somehow. They're not experimentally tested. The only ones that are experimentally tested are the active compounds, and the decoys or inactive compounds are normally generated from a library or something. So many times your machine learning scoring function that you will use to perform visual screening can learn the biases of your data set. So that's a big problem, and I will give you a small example in a few minutes. And again, scoring functions that are trained only to do virtual screening can supposedly show better results than scoring functions that are trained to also do scoring and docking, but it can be difficult to apply those scoring functions to effectively discover new drugs in a system, a protein of interest. So this is one of the examples that the trouble you can run into. This is a very, I think this paper is excellent. It's an old paper, it's 2010 or something like that, I believe. But one of the first applications of machine learning to virtual screening and scoring functions was to take a complex, count how many atom pairs fall within a certain distance of each other, and you generate bins for each type of atom from the protein and the ligand. You measure that and you generate those bins, and you feed that into a random forest or an SVG, different machine learning methods, and those scoring functions were able, here they call them RF-IChem, is random forest, and support vector machine IChem. They were able to, when you plot the experimental binding energy and the predicted binding energy, they were very good at predicting that. The correlation was very high, much higher than, for example, this scoring function here that is surflex doc. Much higher, much higher. And it looked very good, I mean, at the beginning, and other people were doing something similar using the terms of empirical scoring functions, but then instead of adding them together linearly, they put them into a support vector machine or a random forest and predicted binding energies. They were able to perform scoring with a much higher correlation than the original scoring function. But what this paper found is that when you use those same scoring functions to perform docking, then they are terrible. They're very, very bad. They cannot tell a good ligand-protein pose from a bad one. It just has no way to tell which is the experimental structure. It fails to predict that the experimental it fails to predict a global minimum that corresponds to a structure which is similar to the experimental one. Okay, so it has very, very bad docking power. And here you can see that surflex doc had not very good scoring power, but in docking power it had 55% top 1, while these machine learning functions had less than 30% top 1 for docking power. And then when they did virtual screening, the same thing happened. These machine learning functions were very bad at being able to distinguish active and inactive compounds. So what is the problem? Simply that the data that you're training your scoring function on, if it doesn't have the complexity that you will later apply that system to, then it will fail, because you designed that scoring function to do something that is very different to what you are using it for, right? So the scoring functions learn from the data that you give it, right? And it's very hard to get these machine learning scoring functions to actually learn chemistry. So, and another example, here they built a scoring function, a machine learning scoring function, but to do virtual screening. So they use one scoring function to generate the poses, the structures, and then they use a machine learning scoring function to score those poses. And now they try to see how good it is at visual screening. And here you can see on the right side of this graph that this is the ROC AUC, the area under the curve for the receiver operating characteristic curve. And this is one when all the actives are ranked at the top and all the inactives below that. And so a perfect score, a perfect ability to distinguish between actives and inactives equals to a ROC of 1. And here you can see that for the DUE data set that we know it is biased, we get a ROC score of 1. It's perfect. And this is impossible. So you can tell that the machine learning scoring function, what it is actually doing is learning the bias of the data set, right? So I hope this has shown you that it's problematic to train a scoring function to just perform one task. So what we propose and what Marcos told you 2 weeks ago is that we can use data augmentation, automatic derivatives, in combination with batch annealing to train an empirical scoring function to simultaneously optimize the performance of a scoring function for all 3 tasks. And this should generate a scoring function which has a binding energy surface that is the most similar as possible to the experimental one. And it should be good, hopefully good for all 3 tasks. It should be generalizable, it should be quite fast, and it should have very good scoring, docking, and visual screening power. So the take-home message is that limited data sets are available for training empirical scoring functions. The scoring functions trained to perform a specific task should be used with care when used outside their domain. Very promising results for machine learning scoring functions should be cautiously interpreted. Sometimes, if it looks too good to be true, it normally is. It's not good at all. And it is possible to use techniques applied in machine learning to develop new empirical scoring functions. And well, for future work, we are thinking about applying this also to high-graded docking, but I will leave it there. And I would like to thank Marco Villarreal, who is my director. My email is rquiroga at unc.edu.r if you would like to contact me, and thank you to the funding agencies.
Thank you very much, Rodrigo. It was really nice talk, and you learn a lot from your talk and the previous talks given by Mark. And now we'll have the opportunity to have a few questions. Students can address in Portuguese. I guess Rodrigo is going to understand if you don't want to make the question in English, okay? And so, the question. People here in Brazil are very shy, Rodrigo.
That's fine.
Okay. I would like to register. Professor Marcos Villarreal is also here. Thank you very much, Marcos. And I have a few questions. Let's think. When think about one specific docking program, you have a lot of experience with VINA, and when you try to validate a docking protocol to using a crystal structure as a reference, if you keep the same scoring function, the same search algorithm, you still have a lot of parameters that you can think about. For example, the center of the docking box. If you change a little bit of this box, and you can have a terrible results or a very nice result. Only change, tenth of angstroms. Probably you had this experience before. And I think you don't explore this, problem, the doc, a lot. Because you think about the scoring function, you think about the prediction of the bind, the prediction of the position, but you still have room to explore how to address or optimize the doc approach, play around with a very few parameters. I would like to know your opinion about this possibility.
Yeah, you're absolutely right. And normally, what we do, as you say, we approach docking as a local problem. We don't do global docking on the whole protein, but we define a box that normally we try to have encompass all the space of the active site of the enzyme that we are studying. So, but it's true that the bigger you make this box, the harder you make it for the scoring function to find a global minimum that corresponds to the experimental structure. So I think this is also very important, because when you're training a docking function, if your box is too small, it's very easy to find that minimum that corresponds to the experimental structure. And the larger you make that box, the longer it takes, but also you are giving more information, you are exploring a larger part of the binding energy surface of that scoring function for this system. And so there's a balance there between how big you make that box. And of course, if you make that box very small, you know where this ligand has to go. Then any scoring function, as simple or bad as it is, you will still find the experimental structure, right? So yeah, it's a good question, and I think it's something to keep in mind. And I think that for training scoring functions, we should make that box as big as we can, because that means that we are giving more information, in our case, to the training process to eliminate or stop exploring the parameter space that leads to finding global minimums where they should not be.
Thank you very much, Rodrigo. People, feel free to make questions anytime, okay? I'm enjoying to have Rodrigo and Marco here. I guess I set up this set of meet for myself. And I'm not going to explore it a lot. We still have opportunity in future meetings. But I still have one question. Think about, you have to validate every time you're developing a new scoring function. You have to validate to compare what you have published, and also you have to compare, think about docking, RMSD, you have to compare with the crystal structure. From my experience, when you take a look on some of the structures, the data set, even when they use X-ray crystallography resolution as a cutoff, you have a lot of problems with the ligand position. My background is in protein crystallography, and I usually, when I have the data, I take a look at the electron density of the ligand. And most of the time, people who work with doc, they don't care about it. They have the data set, they have a base a database to work, and you still have a lot of problems with the ligand position, because you take that as true. It is not true always. And sometimes we even have two positions possible for the same ligand using protein crystallography. I'd like to know your opinion about it.
Yeah, that's absolutely true, and we are trying to take that into account. One thing was use sucrose instead of RMSD. It's one part that we are trying to do, so that when you have semi-symmetric ligands, sometimes you can find an aromatic nitrogen in the same position, even though it's not the same nitrogen, but you are kind of reproducing the same the same interaction fingerprints, kind of. So that's one part. And the other part, we are also attempting to see, especially for these ligands that have sometimes some atoms exposed to the solvent, we're looking at B factor, and we're looking at the data behind that position, and seeing if we eliminate or don't take into account for the sucrose or the RMSD calculation the atoms that are moving or that can have different positions, because otherwise you would say this didn't dock well, but then you go look at the results, and like that example that I showed, it looks perfect, except for the part that is exposed to the solvent. So yeah, we are taking these things into account, because I think it's very important, because otherwise you are training your scoring function with incorrect data, and you're saying, no, that's wrong, and you're adding that to the loss function, but it's good, it's okay, right? So giving incorrect information will surely make a worse scoring function. So yeah, it's an important point also to make.
Thank you very much, Rodrigo. I appreciate, and I still have a possibility for another people who wants to make any question. So, anybody? Okay. Thank you very much, and we'll keep in touch about our paper. And I'm going to finish the record now.